Alrighty, moving on to chapter 4 now, max and min values. Hopefully you've gone through the Desmos activity already, because I'm not going to spend much time on defining max and min values. And also they're kind of intuitively obvious. But one of the big things that we do in differential calculus is optimization problems, finding the least expensive or the biggest. So these are optimization problems, finding maxes and mins. So you've looked at a lot of pictures on Desmos, and we talk about an absolute max if it's the biggest value anywhere, the absolute min, the smallest value for any number in the domain. They are called extreme values or extrema. Picture, just go through this one really quickly. It has an absolute min at A because nowhere on the graph does it go lower. It has an absolute max at D because nowhere on the graph does it go higher. It has a local max at B because you could circle it and nowhere inside the circle would it go higher. It has local mins at C and at E because you could circle them. And this book goes by the tradition that no local max or min can be at an endpoint. So you have to be able to draw a circle around it, and the entire circle has part of the graph inside of it. So it has to be an interval containing that number for it to be a local max or a local min. It can be both. You can have a local min or max that is an absolute. Okay, so again, I think you've kind of probably got a pretty good idea of those, either just from logic or from the Desmos activity. Example 1 just takes you through cosine. Cosine goes like this. It has a max and min, a max and min, a max and min, and they're all local maxes and absolute maxes, so you can have multiples. I guess the only tricky thing here in this practice problem is the open circle here is not a local max because it's an open circle. It's not in the graph, in the domain of the function. I'm going to leave those for you to do on your own because you did things kind of like that with Desmos. I will write the answers up and put them in the class notes, but I'll do one of these sketching problems before I send you off to do those on your own. Sketch a graph of a function that is continuous on 1, 5 and has the given properties. And number 10, you're going to have to wait till later because you're going to have to know what a critical number is before you can do it. But I'll do number 8 then. I'll take a break and let you do number 9. Yeah, I'll just print out pictures of the other ones and do those on the picture. So we have our function is only going from 1 to 5. So 1, 2, 3, 4, 5. All I need. It has an absolute max at 4. So decide, where do you want your absolute max to be? And put it at the point 4, 4. So I'm never going to allow my graph to get any higher than that. It has an absolute min at 5. So it's going to have to jump way down here at 5. So I'm going to bring it down below the x-axis. It has a local max at 2 and a local min at 3. So my graph's going to look something like that. Yours might be straight lines. it doesn't matter. It doesn't say that it couldn't have other local maxes and mins, but absolutes have to be absolute. So you do have some freedom. I'll leave space for number 9 right here, and I'll draw it. And meet you back here in a minute. Okay, there's my lovely picture choice. We have a local max at 2, an absolute min at 3, an absolute max at 4, and that's it. I did initially have it going down to the axis, and then I realized, oh, well, I guess it would have still been an absolute min. It would have just had 3 absolute mins. I erased it for no reason. I could have left it. Oh well. We'll do number 10 later after we learn what a critical number is. Extreme value theorem. Very important in optimization problems. If f is continuous on a closed interval, then it attains an absolute max and an absolute min somewhere in the interval between A and B. Seems simple. So all it has to be is continuous on a closed interval. Now it only says that it has a max and a min on that interval, not for the entire function, just on that interval. So pictures. From A to B, it's continuous. It has a max right here and a min right here. From A to B, it's continuous. It has a max in the middle and a min at one end. Remember, absolutes can be at endpoints. This one wiggles around. It has a couple of maxes and a min, all in the middle. They could both be at endpoints. It must be continuous on the closed interval, however. Not continuous, there is no max there, because that point, no matter what point you choose, you could get a little bit higher. And it has to be a closed interval, illustrated here, because you could have a vertical asymptote at one end. So, now, extreme value theorem says that it takes on a max and a min, but it does not tell us how to find them. Fermat's theorem helps us with that, however. It appears that at the max and min points, the tangent lines are horizontal. Doesn't mean that every place the tangent line is horizontal gives you a max or a min, but it's a good place to start looking. So Fermat's theorem says, if f has a local max or minimum at C, and if the derivative exists, it must be equal to 0. So, if the derivative exists, it has to be equal to 0. But here is a picture that shows a horizontal tangent line with no max or min. It just flattens out and then kept going in the same direction. Now, here's an example of one that has a min. Obviously, you can see absolute value function has a min at 0, but the derivative does not equal 0 there. That's because it doesn't exist. So you have to be careful when using Fermat's theorem. Just because the derivative is equal to 0 doesn't mean there's a max or a min, and setting the derivative equal to 0 doesn't find all the maxes and mins. We start by looking at critical numbers. Critical number of a function is a number that's in the domain, and either the derivative is equal to 0 or it doesn't exist. If it has a local max or min at that number, then C is a critical number of f. So let's go back and do number 10 that I promised. realize it was so far back. There we go. So again, we're just going from 1 to 5. It has an absolute max at 2. Has an absolute min at 5. So absolute max at 2, I'll put it way up here, an absolute min at 5. I'm going to put it right down here on the axis. 4 is a critical number, but there is not a local max or minimum there. Okay, so how can we make it a critical number that does not have a local max or a min? Well, we can give it a horizontal tangent line. So here, that's what I've decided to make it look like. You can make it look like whatever you want. So remember, horizontal tangent lines. When I drew that one, I made it nice and smooth and curvy. It has horizontal tangent lines at its maxes and mins. This one is not differentiable at its maxes and mins. So either one is a critical number. Okay. Let's get back to where we were. Example 7. Calculate the critical numbers of this function. F of x is x cubed, x to the 3/5, times 4 minus x. Well, we can product rule it, or we can distribute. I think I'll try the product rule. So it would be x to the 3/5 times the derivative of 4 minus x plus 4 minus x times the derivative of x to the 3/5, which is 3/5 of x to the minus 2/5. Now you can see the whole thing. Now let's simplify this a little bit. I know, on your test, I said don't simplify stuff. Now I'm going to make you simplify stuff. 4 minus x is living on top. Let's see, I have a 3 living on top. I have a 5 living down below. And I have x to the 2/5. Well, I'm going to set this thing equal to 0. Actually, first off, I ask myself, where does the derivative not exist? So, f primed is d and e at x equals 0. So that's one place we would look for a max or min. Then we set it equal to 0. So 0 is equal to negative x to the 3/5 plus, I'm going to put the 3 in front, 3 times 4 minus x over 5x to the 2/5. I see something like that and I think, I could cross multiply and solve that. I'm going to move over here. I'll put x to the 3/5 on one side and 3 times 4 minus x over 5x to the 2/5 on the other. Invisible 1, no longer invisible. Cross multiply, I have 5x to the 3/5 times x to the 2/5 gives me x equals 3 times 4 minus x and let's move up here, add 3x to each side, so 8x equals 12. x is 12 over 8, which is 4 goes into that 3 over 2. Let's look at the pretty solution. Oh, look. Critical numbers are 3/2 and 0. This one where the derivative doesn't exist, and this where the derivative is equal to 0.